Hi, welcome to the 8th video on Introduction to Physics in for Neural Network. In this video, we shall see how we can solve the Burgers equation and lid-driven cavity using physics in for neural network. So for Burgers equation, we need some small special treatment to handle it. Otherwise, it's slightly difficult to solve. Anyway, in the first PINN paper, they didn't use any special treatment to solve that equation. They just use a standard neural network approximation to solve the equation. But in this video, we shall see how we can solve the same equation using adaptive viscosity concepts. So in the last video, we saw some of the solution procedures to solve the Burgers equation. In this, we have solved the Burgers equation using finite difference method and finite volume method. Sorry, FTM and FEM. So in that procedure, we saw the importance of artificial viscosity to stabilize the problem. So one way is using the explicit artificial viscosity. In we shall see what is artificial viscosity in the upcoming slide. Another one is using Riemann solvers. Either we use Riemann solvers or artificial viscosity, we will add some viscosity or artificial viscosity to the solver. So this is the viscous Burgers equation. So if we remove this part, this will become invisible Burgers equation. So viscous Burgers equation is relatively easy to solve than the invisible Burgers equation because invisible Burgers equation will produce shock like this. But viscous Burgers equation produce some diffuse shock because of this numerical dissipation. So when we have a sharp shock like step kind of thing, derivative at this point become infinity. But here this won't become infinity. So that we can use the continuous differentiable function as the solution of this partial differential equation. That's why any methods or any numerical methods or PINNs, we will try to smooth this possible. If we don't smooth it, it's almost impossible to solve using most of the existing methods, especially when we use any shock capillary methods and numerical methods or even using PINNs. We know universal function approximation is only valid for differentiable function, but Euler equation which is having shock is non-differentiable. So that will become impossible. That's why we will use adaptive viscosity. So we know this value of the nu plays a bigger role in the smoothness of this shock. So if the nu is very high, instead of having shock, it may become like this. If the nu is very low, or this will become very narrow. If that is very narrow, the gradient value will be very high. So if the value is very high, it's very difficult to stabilize a solver. So we should find an optimal nu which stabilizes the solver. That's the uniqueness of this PINN. It's quite difficult to do on other solvers like numerical methods. What researchers used to do is they come up with some better parameter, better estimation of the new value that works for variety of the flow. So in most of the numerical methods, these are suboptimal. So they may not give the best result, but PINN can give the best result for this problem. So we shall see what are the solution procedures we should follow. So in this thing, we have considered shock like initial condition, step like initial condition, so that we will be getting shock. If we have this kind of shock, if this kind of profile, anyway, over the time, Euler equation will produce a shock because this characteristic intersect with these flows, but it will take some time. But if we have this kind of thing, solution itself having shocks in the profile, so characteristic immediately intersects. So if we have a shock like this, we will be calculating derivative across the shocks. So that is not good. So we will be using viscosity to smoothen this profile. So as usual in PINN, we will be having three losses. One is PDE losses. So we approximate the solution using neural network. Let's say use the solution. We approximate using neural network, which has weights and bias. So this approximate solution should satisfy the initial and boundary condition and PDE. So we will substitute this in Burger's equation and find the PDE loss. Then we calculate the loss like this. The total loss can be the combination of the initial condition loss and boundary so PDE loss. So we can give some weightage W1, W2 to these values. So if we have some issue in stabilizing the solver. In most of my cases, I use uniform weight because I like to spend more time on architecture than working on this thing. But in most of the papers, they don't use uniform weight because I believe boundary condition also have a similar weight to the physics or partial differential equation because boundary condition decides the solution of that. Some cases it's very difficult to do it. Their the neural network may struggle to satisfy the initial and boundary condition. At that time, we likely to give more weightage to the initial and boundary condition. Or in some cases, we may not know the perfect boundary condition. For example, if you do atmospheric simulation, it's very difficult to define the solution variable at the domain boundary or even initial condition. So we always have some uncertainty over the initial and boundary condition. At that time, so based on the problem requirement, we can change the weights. So that's one of the key advantage we will be having when we use the physics informed neural network. So when we substitute that, this is what we'll be getting, and then we can calculate the total loss. Now you may have a question: what is adaptive pain? So one of the brilliant thing in adaptive viscosity pain is the neural network learns the viscosity which can stabilize order. For example, in the last video, when we do a numerical simulation, we found when we use a very low viscosity, very low new value, the solver was destabilized. When we use a very high value of viscosity, we got a bad result, or even most of the cases, a solver will get oscillations. And the solution, we can find a lot of oscillation in the solution. So we can't give the very high new value or we can't give the very low new value. So what we in traditional process I had told, they test on several problems and propose some optimal viscosity for the problem. But in PIN, the neural network itself learned the best viscosity for that. That's the uniqueness of PINs. We can't find this special feature in traditional CMT solvers. Now you may have a question, what is that? So what we already know, we always use a neural network to approximate U. U is approximated using a neural network. Let's say that is NN. Similarly, we will also have another neural network which approximate the viscosity. Maybe I will call it N to N. So either you can use some decoupled network or you can make a neural network. In this case, our input is x comma t and we have a neural network which has several neurons. And not drawing it well. I hope you can understand what it is. Then these are fully connected neural network. Then we have output. The output layer, we supposed to have a U, but instead of that, we can have U1U. So this is output layer. Output layer will be having U and nu. U is a solution, nu is a viscosity for this problem. So the neural network learns its viscosity. So we will have an extra regularization where we ensure mu square should be minimized. Minimized means this minimum value of this is closer to 0. So solver will try to find the optimal viscosity which stabilizes the solver as well as it will try to viscosity as much as possible. So that will be getting a better shock structure. So that's the beauty of this pin. Because of this thing, maybe if we have a well-tuned neural network, it can able to capture the discontinuity on 2 grip points. It's almost impossible with any shock capturing schemes I know. So that's the beauty of PIN. But of course, it has a lot of disadvantage. And maybe once I complete all this tutorial, I will make one separate video on what are the key challenges in PIN and what are the demerits of the PIN, what are the improvement we should do to make a PIN as a better scheme. Otherwise, PIN may not see industrial applications. Fine, I hope you got an idea what is adaptive viscosity. Basically, adaptive viscosity PIN is a concept where neural network itself learn the optimum viscosity to stabilize a solver. Yeah, this is a Burgers equation code. So here we are doing simulation up to 0.2 second. We have taken 100 collocation points on the boundary, added 10,000 collocation points over the domain. So here we have taken -1 to 1. This is just to define upper and lower boundaries. And our simulation is 0 to 0.2. And this is the initial condition. The initial condition that we have used is step-like function like this. Then as usual, we are scaling the values between some limit. In this case, it's not required because we have assigned -1 to 1 as a boundary point. In case if our solution is maybe if our domain is -10 to 100 or something, it's good to scale the domain. Then I already told we will be having two neural network. One is to learn the viscosity, other one is to learn the solution. Of course, you can combine both the neural network and make two output. But in this case, I have preferred two neural network. So this is a neural network. We are initialize the weight using Savior normalization. And then this is a forward pass model. So the second neural network is adaptive PIN is neural network which learns the weight, not weight, that solution U. And this will make a U for NN. So as usual, everything is more or less straightforward because in PIN we don't have much variety of freedoms like numerical methods. Of course, we have variety of pins, we have variety of configuration, variety of pins. What I meant is we have con pin, we have spline pins, Chebyshev pin, and those kind of things. But still, the solution procedure is more or less same. But in numerical methods, they are very diverse. At the same time, they are also very versatile in handling variety of problems. But here we have to do lot of fine tunings. So in this case, we have given 100 weightage to new because so neural network tried to give the diffuse solution. That's why we are penalizing the viscous loss, so that we'll be getting very short result. So other thing is more or less standard, straightforward. If we run this code, we'll be getting a residue value of around 10 power minus 4. And this is a viscosity map for this pin. Finally, this is a solution plot. So this is animation. You can notice that pig can be able to track better than most of the numerical schemes. If we tune it better, it can able to handle the shock on two grid points. Of course, this is not a well optimally tuned pin, but still it's fine because I have made it for just tutorial purpose. So now I hope you got an idea how to solve problem having shocks using pin. So only difference is when we go for problem having shocks, it's good to use the adaptive viscosity pin. In the next tutorial, we will solve Euler equation. When we solve Euler equation, sometimes it's hard to just stabilize the solver using adaptive viscosity. In that case, we will see on another concept that we call the adaptive weight viscosity pin. So now I hope you got a little bit idea how to solve that equation, Burgers equation. I have provided this code in the comment. Please check it. So now we shall see how to solve lid-driven cavity problem using pins. So this is a very famous lid-driven cavity problem. So here we are not making any special treatments. We are just simply solving this problem using standard pin architecture. One of the limitation of this pin is when we try to increase the Reynolds number of the flow, it's very difficult to stabilize the pin solvers. is still one of the biggest bottlenecks in PIN. I hope no one able to achieve 5,000 or 10,000 Reynolds number driven cavity without any data. Probably you can also check it whether it's anybody achieved it or not. When I was doing literature survey a few months ago, I was unable to find any PIN which does not use any data. If you use the genuine data, it's relatively easy. But if you don't use any data, it's very difficult. That's still a bottleneck in PIN. So now we shall see how to solve this problem. So of course, when you try to solve this problem using traditional methods, you need some sophisticated methods like simple, piezo, those kind of methods to solve this problem. And in addition to that, they are slightly or more algorithmic or not straightforward for most of the beginners. But in PIN, everything is very straightforward. At the same time, it has some generalizability issues. If we able to come up, if we remove such bottlenecks in the pins, PIN may become a better solver. So of course, for this problem, our governing equation is continuity equation and momentum equation. So these are the boundary condition. So in lid-driven cavity, I hope everybody familiar with the lid-driven cavity. Just for the time sake, I will briefly explain the test case. Lid-driven cavity will be having fluid inside one lid. The only difference is the lid at the top that will be moving at one particular velocity, moving like this, and we'll be having fluid here. Because of the shear, we'll be getting lot of vortex inside the lid. So this is a problem we'll be solving. So as you know, these are wall boundary condition. I mean, all four sides are wall. Only difference is the top wall is a moving wall with some velocity. So you know, on the wall we'll be having zero velocity. This is a boundary condition we will be applying. Top wall we will be applying U lid velocity. In our test case, we will be using 1 unit or 1 meter per second. Anyway, we have used non-dimensional governing equation, so meter per second doesn't make any sense. You can say 1 unit. So we shall get into the code. So this is very straightforward like other problem. So I'm not going very deep into that because in other problems we have seen most of the steps. There will be a small difference that I will explain. So here we will be giving Reynolds number as the input and U lid as the input. So domain size is 1 unit. So this is a steady state problem. Here we are not considering the effect of the time. So this is a neural network configuration that we have used. So this will be having two input, that is X and Y, and it will drive three output, that is U, V and P. So another good practice, so here we are taking output as UVP. This is a forward of the neural network which will write that UVP as output. Another good practice you can follow is we know pressure cannot become negative if you are dealing with absolute pressure, and density will not become negative. In that case, we can either enforce this pressure and velocity positive through by making it exp exponential, or you can use square of that value, or you can also use ReLU function on the pressure, so that will become always pressure or density. So when we go for incompressible flows, sometimes we may get a negative pressure or density that will destabilize the numerical scheme. So in PIN, we can directly enforce that property. This we call as a positive preserving property in numerical methods. So that we can directly enforce in PIN. But in this code, we didn't use it because this is a very simple test case. In the next test case, we will enforce this property. So as usual, we will be calculating different first derivative, second derivative of velocity and pressure for the Navier-Stokes equation that we have calculated using auto differentiation using PIN. Now we will be substituting those derivatives in continuity momentum equation so that we can calculate the loss. Here we have the boundary losses. Only difference is here we ensure that top wall is moving with the unit velocity. Others are we minimize to 0. So we have sum up all the losses that will constitute the boundary loss. Here we use two algorithms. First we will find the solution using Adams algorithm. Then we will refine the output of the Adams algorithm using LBF-GS optimizer. Because Adam is very fast, after that the solution becomes saturated. So to make it even better, we will feed the output of the Adam to LBGF optimizer. So here we have different collocation points, and this is the PDE loss and this is the boundary loss. After that we are using LBFGS optimizer here. So when we define a LBGF optimizer, we should define a closure function. The closure function is nothing, the loss function, what we are feeding. So that's what we have created here. So this is a PDE loss, and this will create losses for boundary top and every other boundaries. Then we are calculating loss using this formula, 1 into PD into loss. Anyway, here we are using this thing because our final iteration is on LBGF, where we have given equal weightage to PDE and boundary. So whenever we are calling this LBGF optimizer, we should give the closure equation to the argument to the optimizer, LBGF optimizer. For Adams, that's not required because Adams just work on the parameters of the optimization algorithm. But LBGF need both parameter as well as optimizer. Sorry, objective of the objective function. So here we have used 10,000 collocation points in boundary and through the domain. After that, we are having different plotting function. Finally, we are comparing our result with a Gaia paper on retrieval cavity. So once we train this algorithm, this is what we get. This is a U velocity plot, V velocity plot, and this is a pressure plot. We can notice that when we use Adams optimizer, after some epochs, it becomes saturated. Then when we go to LBGF optimizer, we got a even sharp drop in the residue. After that, it becomes saturated. If you want even better result, you may club it with even higher order optimizer and make it better. Because it's just a tutorial problem, I just used two algorithms. Even with these things, we got some reasonably okay result. So here we have compared that PINN solution with a Gaia et al. Result. So this is a U velocity plot at x is equal to 0.5 location. And this is a Y velocity plot at y is equal to 0.5 location. You can try with different high Reynolds number and check how well this is work. So basically this simple architecture won't work for high Reynolds number flow. We need some specialized architecture. Of course, even best architecture may not able to handle very high Reynolds number, like I said, or 5,000 or 10,000. Maybe if you use some Fourier inputting and those things, you can slightly push that limit. People are doing a lot of research how to make it better. Probably if you have some better idea or something, you can try and you can remove these bottlenecks. I hope today you have enjoyed today's video. So in the next video, we shall see how to solve Euler equation using PINNs. Thank you for watching.